It is indeed permissible to use a delta to Y transformation for calculation purposes, and it's a widely accepted practice in electrical engineering due to its ability to simplify complex circuit analysis. Essentially, you are converting a delta, also known as a pi network, to an equivalent Y, also known as a T network, simplifying the math without changing the overall behavior of the circuit as seen from its terminals. The conversion formulas are as follows. Firstly, SO equals ZB times ZC divided by the quantity ZB plus ZC plus SO. Secondly, ZB equals SO times ZC divided by the quantity ZB plus ZC plus SO. Thirdly, ZC equals SO times ZB divided by the quantity ZB plus ZC plus SO. These formulas enable you to determine the equivalent Y impedance values based on the delta impedance values. It's essential to apply these formulas accurately to maintain the electrical equivalence between the two networks. After converting your delta network to a Y network, you can proceed with your calculations as if you were analyzing a standard Y-connected circuit, which can significantly simplify the process. It's a key point to remember that a delta to Y transformation does not alter the overall impedance seen at the terminals of the network. The total impedance calculated in the Y configuration should match the total impedance of the original delta configuration. Let's go through an example. Imagine a delta-connected circuit with the following impedances: SO equals 10 ohms, CB equals 15 ohms, and ZC equals 20 ohms. To convert this to a Y configuration, we apply the formulas. Firstly, for the calculation of SO, we have SO equals the quantity ZB times ZC divided by the quantity ZB plus ZC plus SO, which translates to 15 ohms times 20 ohms divided by 15 ohms plus 20 ohms plus 10 ohms. Simplifying this, we get 300 ohms squared divided by 45 ohms, which equals 6.67 ohms. Secondly, for the calculation of ZB, we have ZB equals the quantity SO times ZC divided by the quantity ZB plus ZC plus SO, which is 10 ohms times 20 ohms divided by 15 ohms plus 20 ohms plus 10 ohms. This gives us 200 ohms squared divided by 45 ohms, which equals 4.44 ohms. Thirdly, for the calculation of ZC, we have ZC equals the quantity SO times ZB divided by the quantity ZB plus ZC plus SO, which is 10 ohms times 15 ohms divided by 15 ohms plus 20 ohms plus 10 ohms. This simplifies to 150 ohms squared divided by 45 ohms, which equals 3.33 ohms. To confirm that the transformation didn't change the overall impedance, let's calculate the total impedance of the Y network by summing the individual impedances. D total equals SO plus ZB plus ZC, which is 6.67 ohms plus 4.44 ohms plus 3.33 ohms, resulting in a total impedance of 14.44 ohms. For the delta network's total impedance calculation, this requires a different methodology. To get the line-to-line impedance of the delta network, you need to consider the parallel combination of SO in series with CB and ZC. The equivalent impedance between two terminals of the delta network would be the parallel combination of ZC and the series combination of SO and CB. So, series equals SO plus CB, which is 10 ohms plus 15 ohms, which equals 25 ohms. Now calculate the parallel impedance. C parallel equals ZC times series divided by ZC plus series, which is 20 ohms times 25 ohms divided by 20 ohms plus 25 ohms. This gives us 500 ohms squared divided by 45 ohms, which equals 11.11 ohms. This impedance represents the impedance between two terminals of the delta network. Since there are three possible pairs of terminals in the delta network, and each calculation will yield a different value depending on which impedances are used, there is not a single total impedance for the delta network in the same way there is for the Y network. Instead, the input impedance depends on where you are measuring it from. Note that the line-to-line impedance of the equivalent Y network is not simply the sum of the impedances as it was when looking at the impedance from the neutral point. The impedance from one line to another in the Y network is the sum of the two series impedances. In this case, between the line with the 6.67 ohms impedance and the line with the 4.44 ohms impedance, the total line-to-line impedance is 11.11 ohms. In summary, the delta to Y transformation is a powerful tool for simplifying circuit calculations, enabling engineers to analyze complex networks more efficiently. However, it's crucial to apply the transformation formulas correctly and understand the relationship between the impedances in both configurations to maintain the accuracy of the results.